Hello. In the last part, we have discussed about amortized analysis. Very brief introduction about amortized analysis, and we saw that we can perform amortized analysis on the operations of any data structure. Right now, we also see that there are three techniques of amortized analysis. These are aggregate analysis, accounting method, and potential method. Now, out of these three techniques, we are going to explore the aggregate analysis in this part. Okay. So what we do in when we are perform aggregate analysis on the operations of a data structure. So we first determine the worst case upper bound on the total cost of a sequence of n operations. Okay. So in spite of considering a single operation and finding out what will be the its performance or what will be the complexity of that algorithm when the scenario is worst, rather what we are doing here, we are considering a sequence of n operations on the data structure, and these operations include all the operations available for the data structure. Means if we consider stack as a data structure and the available operations are push and pop, right? So when we are doing aggregate analysis, we'll consider a sequence of n operations which contains push operations and pop operations. Okay, so it can be in any order, but total number of operations will be n. Okay, so it is possible that all of them are push operations. It is also possible that all of them are pop operations, or it is also possible that they are interleaved, right? Push, pop, and in any order. Okay. So once we determine the sequence of these n operations, next we have to find out what will be the upper bound, worst case upper bound for this sequence of n operations. Okay, so what will be the total cost for this sequence of n operations? We have to find out the worst case upper bound on that total cost. Okay, so if we consider Tn be the total cost for this sequence of n operation, then we are going to tell that the amortized cost of each operations that are involved in the sequence of n operations is basically Tn by n. Okay, or in other terms, since n operations are taking in total Tn time, then each operation is going to take Tn by n, the average time. Okay, so that average time is basically amortized complexity or amortized cost of all the operations that are used in the sequence of n operations. Okay, so that is why it is told that the irrespective of the type of operation, this amortized cost is assigned. So as in the example of the stack, we have push and pop operation, and we have a sequence of n push and pop operations, and once we perform the analysis and we found that the Tn is the total cost, and then we'll tell that the amortized cost of push is Tn by n, and amortized cost of pop is Tn by n as well. Okay, so all the operations over there is basically having the same amortized cost. Okay, so this is the scenario or this is the case for the aggregate analysis. Means in aggregate analysis, all the operations are basically having the same amortized cost, which are nothing but the average on the n operations, average of total cost on the n operations. Okay, but this is in case of accounting method or potential method, we can have different amortized cost for different operations. Okay, but for aggregate analysis, we will have same cost over all the operations. Now let us take an example to understand this. So as I told you in the previous lecture, that we will have two example. One is of stack operations, another is of binary counter, and we'll explore explore the three techniques using these two example, right? So so in this part we are going to give you the example of the stack operations. In the next part we are going to discuss the binary counter example. Okay, so in stack operations, so let us consider a stack. Okay, so what are the operations available for a stack? So for a stack data structure, we have two operations available. The first one being push. Using this operation, what we do, we basically push an element on the stack, right? And this operation takes order of 1 times. And another operation is pop, right? So using this operation, what we do, we are basically we pop out the top object from the stack, right? using pop operation, and it also have the same complexity of order of 1. So these are the two operations that are available with stack. To explain the aggregate analysis, let us consider there is also another operation that are available with the stack data structure, and we'll call it as multipop. So what multipop will do, it will basically take two arguments as input. One is the stack, another is a positive integer k, and it will try to pop out top k object from the stack. Okay, so it will try to bring out all the top k objects from the stack. Now in such while doing that, it may be a scenario that the element that are available in the stack is less than the value of k, right? So what will happen in that case? So when the value of k is greater than the number of element available in the stack, then it is going to pop out all the items. Okay, so it is going to pop out all the items if k is greater than size of s. Now size of s does not mean the maximum number of elements that the stack can hold, or in other terms, size of s does not mean the capacity of the stack. Rather, it is denoting the number of elements currently present at stack. Okay, so that is denoted by size of s. So now with this description of multiple operation, what we can do, we can define an algorithm for multiple operation, right? So this is what the algorithm for multiple operation will look like. So in that operation, what we have two input, s the stack and k a positive integer, and we are checking in the algorithm, we are basically checking while stack is not empty and k greater than 0. Okay, when these two conditions are true, then what we are going to do, we are going to pop one element from the stack, and we are reducing the value of k by 1. So what this algorithm is telling, the algorithm is telling that we'll basically keep on popping one element and reducing the value of k by 1 until either stack becomes empty or k becomes 0. So if you look at the description of the multiple operation on the left, so there are two ways the multiple operation can perform. Either if there are enough elements, then it can pop out all the k objects, but if there are not enough elements, it will then pop out all the object from the stack, right? So that is, it will make the stack empty. So if you look at the algorithm on the right side now, so you will find out that until the stack become empty and k become 0, so if either of the condition become false, the algorithm will stop at that point, right? So what will happen, when there are enough element, okay, so when there are enough element, we are going to pop out one item from the stack, and we are reducing k value of k by 1. So when there are enough element, what will happen, the value of k will eventually become 0, but there will be some element remaining on the stack, right? So that will basically gives us the case when k is less than size of stack. And if there is not enough element, then what will happen, then in the same scenario, the stack will become empty before k becomes 0, right? So in that case also, the multipop operation will not continue the rest of the iteration for the value of k to become 0. Rather, it will, as soon as the stack becomes empty, it will get out of the loop, right? So suppose if we give an empty stack, and if you give any value of k, so it will never get into the while loop, right, if the stack is empty. Okay, with this definition of the algorithm, now if I ask you what will be the complexity of this multipop operation. Now if you look at this algorithm, and if you perform the worst case analysis, in the worst case, what will happen? In the worst case, it might happen that the stack is full. Okay, it has all the element up to its capacity, and you are calling the multipop operation to pull out all those elements. Okay, so at that case, the while loop is going to be executed the maximum number of times, which is basically the capacity of the stack, right? So that is nothing but if there are a maximum, if the stack can contain maximum n elements, then we can tell that the complexity of multipop operation in worst case is order of n, right? But if we try to be a kind of exact or a bit tighter value for this complexity, what we have, see, I mean how much time the loop will be executed, that is basically deciding the complexity of the multipop operation, right? So the loop will be executed either till the point either stack becomes empty or k becomes 0, right? So whichever becomes first, either of them can become first, right? So if any of them become first, the multipop operation will halt, right? So which one will become first? That one will become first which is having the less value, right? So a tighter complexity for this algorithm can be defined by the minimum of k and size of s, right? So whichever is less, and that number of time the while loop will be executed, and after that the multipop operation will be terminated, right? So minimum of k and size of s is basically defining the tighter complexity for this multipop operation. Okay. So now let us try to see how the aggregate analysis work. Okay, so while we are performing aggregate analysis, as I already told you, we are going to analyze a sequence of n operations, right? So in the stack now we have three operations: push, pop, and multipop, right? So we'll have a sequence of this n push, pop, and multipop operation, and initially we'll have an empty stack, okay, on which we are going to perform this operation. Now what we are going to do, now we are going to let us first see what will happen in such scenario if we perform the worst case analysis. Okay, so in worst case analysis, now we are trying to find out how much time or what will be the upper bound given by the worst case analysis for the total sequence of n operations. Okay, now if we analyze the way we do in the worst case analysis, we will find that the worst case method for a multipop operation is nothing but order of n, right? So in worst case, multipop operation takes order of n time. Now the stack has only three operations: push, pop, and multipop. So out of those three operations, we can tell that the worst case of any stack operation is taking order of n, right? Push is taking order of 1, pop is taking order of 1 in worst case, but multipop is taking order of n in worst case, right? So in any stack operations, right? So in any stack operations is the worst case for any stack operations is nothing but the order of n, which is given by the multipop operation, right? So what we will tell in worst case analysis, we will tell that since the worst case of any stack operation is order of n, and we have sequence of n operations, so in total it will going to take order of n square time, or n times order of n time, n times order of n, that is order of n square. Okay, so a sequence of n operations is going to take order of n square time, right? Now let us look how we will do the aggregate analysis. Okay, so when we are trying to perform aggregate analysis, what we will do, we will try to find out what is the exact number of operation, or an upper bound on the exact number of operations that are going to happen. Okay, so if we try to think, we will find that we can pop an object from a stack at most once after it is pushed, right? So each object in an stack can be popped at most one after it is pushed. So you can only pop an element from a stack if it is pushed. If it is not pushed, it is not in the stack, you cannot pop it out. But if it is in the stack, it means that you have already pushed it, right? But you can pop it at most once, you cannot pop it more than once, right? So each operation can be popped at most once after it is pushed. Now when we are trying to analyze the sequence of n operations, what we can tell, that so the number of times the pop operation can be called, and which includes the call of multipop. Now if you remember the algorithm of the multipop, in the algorithm we are calling, or we are using the pop operation, right? So the total number of pop operation that can be called effectively is being upper bounded by the push operations, right? Because you can pop only those items that you have pushed, so you cannot pop more item than the item you have pushed, right? So the number of pop operation including the pop operation from the multi-pop, is being upper bounded by the number of push operations. Okay, that the pop operation has to be less than or equals to the push operations. Okay, and again this push operation is being upper bounded by n, where n is the sequence of n operations. Okay, so since we are considering n operations sequentially, so we can have at most n push operations, right? Because we are considering n operations, so we can have any number of push operations that is less than or equals to n. So what we have in this point, we are telling that the number of pop operations, including the calls from the multi-pop, is being upper bounded by the number of push operations, which is again upper bounded by the total number of operations in the sequence, which is n. Okay. So now what we can tell, therefore any sequence of n stack operations will take order of n time in total. How? So if we consider now let us consider this any sequence of n operations. So what we can have n push operations, right? Now n push operations will take order of n time. I mean each push operation will take order of 1, then n push operation is going to take order of n time. So if the n sequence of n operations contains only push operations, then it is taking order of n. Similarly, you can also consider like first half of the first n by 2 operations in the sequence is push and next n by 2 is pop, right? So if first n by 2 operations are push and the next n by 2 operation is pop, or operations are pop, then what will be the total time taken by this sequence of n operations? So n by 2 push operations will take n by 2 times, because every push operation is taking order of 1, and similarly every pop operation is taking order of 1. So n by 2 pop operation will take n by 2 time. So in total it will take n time, which is basically order of n, right? So this is nothing but order of n. In the worst case, you can tell that it might happen. So when will be the worst case? And the worst case will be the scenario when we have pushed the maximum number of elements and pulled out or popped out maximum number of elements, and that is possible when out of this n operation, first n minus 1 operations are push operation, right? So if the first n minus 1 operation is the push operation, it means it is going to push n minus 1 items in the stack one by one, right? For this one operation, and the time it is going to take is nothing but n minus 1, right? Now the remaining one operation in the sequence, let us tell it is multi-pop operation. Okay, and I am writing in abbreviation is MP. So this one, suppose it is multi-pop operation MP, and it is going to pop out all the elements from the stack, right? So there are n minus 1 element in the stack after n minus 1 operations, and in the last operation we are going to pop out all those elements. So in the last operation, the multi-pop operation is basically going to execute the loop n minus 1 times, right? So it will take n minus 1 times for execution. So the total time taken by these n operations is going to be twice into 2 into n minus 1, right? Which is again order of 1, right? Which is again order of n. Okay, so therefore any sequence of n stack operation takes order of n time in total. So any combination you take, you will find that this operation is going to be order of n in total, and hence what we will tell, we will find out the average time. So the average time is going to be order of n divided by n, or order of 1. So we are going to tell that the amortized cost for each operation, that is push, pop and multi-pop operation, is going to be order of n divided by n, or order of 1. Okay, so the amortized cost of push is order of 1, amortized cost of pop is order of 1, and amortized cost of multi-pop is also order of 1. Okay, so you can see the difference. In worst case analysis, you have found that the cost of multi-pop operation, that is not amortized cost. The cost of multi-pop operation is order of n. But in case of aggregate analysis, where we or amortized analysis, we found that the cost of multi-pop operation is order of 1. Okay, so this is how we perform the aggregate analysis. So in the next part, we are going to see another example of binary counter, and we are going to do the aggregate analysis on binary counter in the next part.